All right, let's talk about polarizing by reflection. So this is the second half of kind of the polarization discussion. So partial polarization. This occurs when light reflects off shiny surfaces. So after the reflection, the component of the electric field parallel to the surface is reflected and unchanged. So let's talk about what that would look like. So I'm going to have my unpolarized light, which means I'm going to draw light in this kind of fashion here. So I'm going to just create this design here. The green lines represent all the different axes that the light is approaching the surface at. So that's unpolarized light. When the light strikes that surface, so we've got medium 1 and medium 2. Medium 1, medium 2. What will happen is that if it's a shiny surface, then the light waves that are fluctuating parallel to the mediums or the interface will be reflected. So we get this kind of reflection, and the result is polarized light. Okay, so polarized light. And this is an example of total polarization. All right, so this is ideal. So in order for that to happen, we have to have the light, the unpolarized light, strike at a particular angle, and I'll talk about that in a second. So this is the unique situation. This is ideal, I guess, if you're looking for polarizing light off of a shiny surface. What happens to the rest of the light? Well, if it's, let's say, air and water, so let's think of yourself out on a boat or out on the beach, and you've got that sharp glare coming off the water. It's because of that polarized light reflecting. All right. Now, we know we can still see underwater, which means light needs to pass through. It means that the light waves that were not parallel to that surface have passed through. So you'll notice that that missing component right here is actually been reflected, creating that polarized light. So that's what's happening when you have that glare coming off of water, off snow, anything that has that shiny surface, or off glass of oncoming traffic. All right. So how do you determine when that occurs? So 100% polarization by reflection occurs when we have something called Brewster's angle. And Brewster's angle is calculated by tan theta equals N2 over N1. And remember, N is your index of refraction. So a quick example with this, we have at what angle, calculate the angle at which all of the reflected light is 100% polarized out of glass to water. So what happens is we have glass, we have water, and we have our unpolarized light coming down to the surface, and similar to refraction, we are looking for that angle right there. So that tells us when we would get that perfectly polarized light reflected off, and then your remaining light entering into the water itself. So our formula for Brewster's angle, N2 over N1. So N2 is always the material it's entering. All right. Material being entered. So we have Brewster's angle equals tan inverse of 1.33 divided by 1.5. So the angle would be 41.6 degrees. So light has to approach or strike the interface, so it would have to come in the glass at an angle of 41.6 degrees, strike the water, and you'd end up with total polarization. Anything off of that angle, you're not going to get complete polarization. You're going to get reflection, partial reflection. The closer you are to that angle, the more polarized the light will become. So that will give you total polarization. All right. So that is when you're looking at, like I said, surfaces like light reflecting off water, snow, glass, etc. Okay, so an application of polarization. Now there is a whole bunch of them. I've added this in here. This is how LCDs work. I'm just going to go through it briefly, and you will be able to investigate a little bit more on your own. Some of the more common ones, sunglasses. Your more high-end glasses, the more expensive the glasses are, the more they're polarized to reduce that intensity. I'm not really going to go beyond that because I'm just kind of talking about them. Tint on windows. Okay, gets rid of the glare. So the tint on your window has some kind of polarization agent. Someone earlier in the course, they were kind of into cameras, camera buff, and they said the camera lenses are polarized. What it does is it reduces the glare reflection off whatever they're taking the picture of. Okay. Now I've taken this picture off of Google Images here, and it's to show you what's involved in your LCD TV. So that LCD TV has a whole bunch of components. I'm not going to go into the huge detail of it because it's a little bit more complicated. I just want to simplify it a little bit. So you'll notice the highlights are key for me here is that there are 2 polarizing films in an LCD. There's one right here, and then there's one right here. So we have 2 polarizing films. What you'll notice when you take a close look at my picture here is that they are oriented perpendicular to each other. So if you look, this one is oriented vertically, this one's oriented horizontally. So you would think that light that's coming through here to project on your LCD, there should be nothing at all projecting on it. Well, what this liquid crystal layer does, okay, it will twist the light wave. So that liquid crystal layer will twist the light wave because it will want to align the light wave to the components or the particles that make up the LCD. So in this region here, it will twist that light wave so that it is aligned horizontally. So that means that the light wave, I'll cheat a little bit here, it's drawn like that. Once it goes through, it's now oriented the other direction. So now you're thinking, okay, well that makes no sense because that means all the light will get through. Well, the key then is, or the final key component for me here is that the positive electrode. What happens is when these regions, you'll notice that they're boxed up. All right, these little electrodes, there's a series of boxes, so it's like a mesh. You can charge individual areas. So when that electrode, when LCD is, I'll use the word charged. Again, I'm just keeping it simple here. The light wave is untwisted. Untwisted. So that means it goes back to its original orientation and therefore will be blocked by the second polarizing film. So the LCD actually is all the light striking the screen, and what makes up that, in this case the 6, is light not reaching the LCD's display. So those particular regions then, this is where light would have been blocked. So the light striking here would have been perpendicular, same thing here. So this orientation, that's where the light waves got blocked. And the reason is because when they came through here, that charge untwisted the light wave and had it strike it. So LCDs are a prime example of where you would see Polaroids. Most of you have probably heard of Polaroid sunglasses. And like I said, tint, camera lens, and probably you guys could come up with a bunch more. There's the assigned homework. Please note for the homework, the following, you should have this formula already on that cheat sheet. Index is speed of light divided by the speed in the medium. And also, our index for an air is 1.0. If you have any questions, make sure you ask them. If you want anything, investigate further explanation, we can talk about it in class. Just got to ask, and I will attempt to deliver.